Okay, this is your instructor again, Tom Perepsky, and we're still in Module 9 on hypothesis testing. And this time we're going to take up a test on a population variance. So far we've learned about testing hypotheses about means and proportions, but we haven't had much to say about variances. There will be situations where we want to test a hypothesis about a population variance, sigma squared, or we could also do a test on a standard deviation sigma, since it's just the square root of sigma squared. As always, we need our best point estimator, and the sample variance S squared is our best point estimator of sigma squared. One of the reasons why we haven't done much with variances yet is that the sampling distribution of S squared is not a normal distribution like X bar or P bar were. You'll recall in Module 7 you learned that the distribution of X bar and the distribution of P bar are normally distributed under certain conditions. But that's not true with S squared. However, the distribution of S squared is related to another mathematical distribution that's called the chi-square distribution. This is the Greek letter chi down here, and then we put a square on it, so we call it chi-squared. Like the t distribution, chi-squared is identified by its degrees of freedom. As usual, we're going to have different forms to the hypotheses. We can have either a right-tailed or left-tailed test. A one-sided right-tailed test would look like this. Is the population variance less than or equal to some value, which we'll call sigma 0 squared, or is it above that value? We could have a one-sided left-tailed test. Is the population variance greater than or equal to sigma 0 squared, or is it less than sigma 0 squared? And finally, we could have a two-tailed or two-sided test. Is the variance equal to sigma 0 squared, or is it not? As always, notice that the equality portion has to be in the null. It could be a greater than equal, or less than or equal, or an equal, but we need the equals part in the null hypothesis. We need a specific testing point. The alternative can be either a greater than, less than, or not equal to. Now, as always, we need a test statistic. Except unlike when we did means and proportions where we had the z and t statistics, this time the test statistic is going to be what's called a chi-square statistic. It can be shown in mathematics that the ratio n-1 s squared over sigma squared gives you a chi-square distribution with n-1 degrees of freedom. So when we're talking about a hypothesis test, we will substitute sigma 0 squared in the denominator here. That'll be our hypothesized value. We'll go out and take a sample of n items. We'll have to calculate our sample variance, and then put it all in here to get our calculated chi-square value. Then, using the critical value approach, we'll have to compare that calculated chi-square to a critical value off the chi-square table and make our decision. A little note at the bottom here. Technically, this chi-square procedure requires that you're sampling from a normal population. This is what a chi-square distribution kind of looks like. It's generally positively skewed. It actually changes shape with the degrees of freedom, but we don't need to worry about that. Notice it starts at 0, so there's no negative values like there is on the t distribution or the z distribution. So that means if we're doing a two-sided test, we're going to have to find two different chi-square values that won't just be the positive and negative of one another, that leave alpha over 2 in each end. This is a portion of the chi-square table that should also be in your textbook. Like the t distribution table, notice at the top it says area in the upper tail of the chi-square distribution. Down the left we have the degrees of freedom that we need. Out in the middle you have the chi-square values. Now the strange thing you might notice about this is notice we have a lot more columns than we did in the t-table. Notice that some of these probabilities are very small, and then suddenly it jumps up to the large ones. The small ones, of course, are going to be on the right tail of the distribution. For example, this column here would be chi-square values that leave a 10% probability above it to the right of it. These larger probabilities are the ones in the left end of the chi-square, because the table still gives you the probability to the right of the chi-square value. So if I looked in the 0.95 column, I'd be getting a chi-square value that leaves 95% of the area to the right of it with the appropriate degrees of freedom. So keep that in mind as we do a couple of examples. Our decision rule, and we're only going to do the critical value approach with this test. I'll talk about that at the end. As always, we need to compare our calculated chi-square to a critical value. If you have a right-sided test, we're going to reject the null if we get a calculated chi-square that's greater than chi-square alpha, which means the chi-square value that leaves an alpha probability above it. Left-sided test will reject the null if we get a chi-square less than the chi-square value that leaves 1 minus alpha to the right of it, because 1 minus alpha to the right of it would mean alpha probability to the left of it, which is what we want. Two-sided, we're going to reject in both ends of the distribution. On the right-hand side, we have this if chi-squared is above chi-squared alpha over 2. In the left end, we have this if chi-squared is less than chi-squared 1 minus alpha over 2. Again, get used to this notation. When I say chi-squared alpha, it means the chi-squared value that leaves an alpha probability to the right of that value. This is kind of what the chi-square distribution looks like, generally positively skewed, as we looked at a minute ago. So if I had a right-tailed test, I'm going to have to find a critical value up here in the right end that leaves alpha probability above it. So I would look in the column for whatever alpha level I want. If I have a left-tailed test, my critical value is down here, and I'll reject to the left of it. But again, the table gives you the probability above this value, so you'd have to look in the chi-square table that leaves a 1 minus alpha probability to the right of it. And if you had a two-sided test, we'd have to find both of these. Cut alpha in half, find the upper chi-square that leaves an alpha over 2 probability to the right of it, and find what I call the lower chi-square down here that leaves a 1 minus alpha over 2 probability to the right of it. Let's do a problem. Actually, we're going to do a couple. Assume the distribution of wait times that customers face at a grocery store is normally distributed. In the past, studies had shown that the standard deviation of wait times was 5 minutes, which would translate into a variance of 25 minutes. With new technology, management believes that the variance in wait times has decreased. We take a random sample of 20 customers. We get a sample variance of 9 minutes. Use a 5% level of significance and test whether or not the variance in wait times has in fact decreased. Once again, we have to read the problem carefully to get our hypotheses. The variance was 25 minutes in the past, and now we want to know, has it decreased? Well, that tells us right away that we have a one-sided test, and it's going to be a left-tailed test. The null hypothesis is going to be the way things were in the past. The variance was 25 minutes. And now, due to new technology, we're hoping that that variance in wait times has decreased below 25 minutes. Use a 5% alpha level. We calculate our test statistic, the chi-square statistic. N minus 1 is 19. S squared was 9. The hypothesized value of sigma squared is up here, 25. Work that out, you will get 6.84. We now need to compare that 6.84 to a critical chi-square value. So we need our decision rule. Again, since this is a left-tailed test, we will reject in the left end of the chi-square distribution. If you go to your chi-square table with 18 degrees of freedom, you will find the critical chi-square to be 10.117. And if you're not sure about that, we'll show you that in a moment. So I'm going to reject the null if I get a chi-square below 10.117. Remember, our calculated chi-square was 6.84, so that is below 10.117, so we reject the null. By rejecting the null, we are concluding that the variance in wait times has decreased. Take a look at this graphically. It's a left-sided test, so the rejection area is going to be in the left end of the distribution. Our critical chi-square is 10.117, and again, I'm going to go to the table in a moment to show that to you. So we would reject the null for anything below there, and 6.84 falls into that range. It is below 10.117. To find that critical chi-square, remember on this problem we had 19 degrees of freedom. We want a value in the lower end of the chi-square that leaves 5% below it, which means 95% above it. So go to the 0.95 column, down to 19 degrees of freedom, and that's where you got that critical chi-square value, 10.117. That's where this came from, and on our graph. Okay, we're going to do one more similar problem, but this one will be a right-sided or right-tailed problem. For many industrial products, variance in the weights of the products can be crucial to the quality of the product. For one product, the variance should be no more than 200 grams. A variance that exceeds 200 would indicate a production problem, and some corrective measure would need to be taken. Quality control took a sample of 18 units, so that's our sample size. We got a sample standard deviation of 16 grams, and if that's the standard deviation, then the variance, the sample variance, would be 16 squared, which is 256. Test whether or not the variance in weights exceeds the standard. Use a 5% level of significance. Once again, we need our hypotheses. The variance should be no more than 200, which means it should be less than or equal to 200. And we want to test our research hypothesis will be, does the variance exceed that standard? That gives us these hypotheses here. The null is the standard. The variance should be less than or equal to 200 grams. The alternative, the research hypothesis, we're concerned about the possibility is the variance greater than 200 grams. Again, we're going to use a 5% alpha level, calculate our test statistic. N was 18, so n minus 1 is 17. S squared was 16 squared, or 256. Our hypothesized value of the variance is 200, so that goes in the denominator. And this turns out to be a chi-square value of 21.76. Again, we need to compare that to a critical value in the upper end, the right tail of the chi-square distribution. With 5% level of significance, that chi-square value happens to be 27.587. Let me show you quickly where that came from. We had n minus 1 to be 17 degrees of freedom. Go over to the 0.05 column, and there's our critical chi-square, 27.587. Compare your calculated value of 21.764, which we had gotten right back here. I think I just took it out one extra decimal. Notice that our calculated value is less than the critical value. Therefore, we are unable to reject the null. And therefore, we are unable to state that the variance in the weights exceeds standards. And here's a little diagram of this problem. Here's our hypotheses. It's a right-tailed test. We're going to reject if we get something greater than 27.587, if we get a chi-square value above there, but we did not get that. Okay, notice as I mentioned earlier, we're not going to use the p-value approach here. Mostly that's because the chi-square table, similar to the t-table, it's kind of difficult to find p-values on that table. You cannot get the precise value. And also, maybe more importantly, the chi-square test of variances is not in most calculators. So you wouldn't be able to get the exact p-value that way either. So we'll just use the critical value approach here. And that's all we're going to do with variances, and that's the end of Module 9. In the next module, we're going to take up differences in means.